In this section, section 10.4 of our book, what is a functional group? You know, earlier we stated that there are over 10 million organic compounds that have either been discovered or synthesized by organic chemists. And it might seem as an impossible task to learn the physical and chemical properties of so many compounds. So what we've done is begin to categorize based on the structural formulas that these common families have together. They've been put into groups of families based on what's called a functional group. To define that, it's known as an atom or group of atoms within a molecule that show a characteristic set of predictable physical and chemical properties. It's the functional group of the organic molecule that undergoes the types of chemical reactions that we're able to study and predict. So although organic compounds can undergo a wide variety of chemical reactions, only certain portions of their structures undergo that chemical transformation. That specific region that undergoes that predictable reaction is known as its functional group. We're going to begin looking at each one of those functional groups one at a time. And then again, specifically in further chapters. So kind of functional group theme as we proceed through this course. We know functional groups are also important because they contain units by which we divide the organic compounds into the families of. And for example, we can look at an alcohol or an amine or an aldehyde and see certain characteristics that belong to every compound that contains that same functional group. So as we take a look at functional group and understand their importance, we understand that they undergo the same type of chemical reactions. No matter what it's bound to or where it's found, that family of reaction can be used to predict products. To a large measure, they determine the chemical and physical properties of a molecule. They are the units by which we divide organic compounds into families, and they do provide us with the basis on which we derive names. So the whole entire category of nomenclature is based on the functional group of that molecule. Here is a list of not all, but some common functional groups. We have an alcohol family. When I see an alcohol family, I'm going to notice that there is an OH on the functional group's last name. Let me back that up, sorry. So with a functional group, let me get my pen. If I see an OH attached to a hydrocarbon, such as an ethanol, CH3CH2OH, this makes it an alcohol. An amine. Amine has a functional group NH2. Here's ethylamine or ethanamine, CH3CH2NH2, the functional group. An aldehyde has a C double bond O at the end of a carbonyl chain, and we'll see its nomenclature relies on an AL ending. Ethanol. In an aldehyde, ethanal, ethanol. Hear the difference? OL, ethanol, ethanal. Very close, isn't it? A ketone now has that carbon double bond oxygen in somewhere other than the final carbon. So it's somewhere within the structure. Here is the C double bond O not at the end, making it a ketone. Acetone, nail polish remover, is an example there. Carboxylic acids such as acetic acid, COOH, remember that COOH gives it its functional group. If you see that molecular formula written COOH, COOH. And then carboxylic esters. An ester, we have a carbon double bond O and then the oxygen, but then instead of a hydrogen here, which would make it an acid, we have what's called an R group, and an R group is just whatever hydrocarbon chain is placed after that oxygen. Here we have ethyl acetate. Ethyl, 2 carbons on both sides, and then this functional group, COO, making it a carboxylic ester. Now, this is just a handy chart that allows us to kind of introduce the 6 common functional groups, but we'll talk about specifically one family at a time. Functional groups are those things that are placed on the carbon chain, the carbon backbone, that allows us to begin to categorize by families certain common traits of certain organic compounds. So they are the sites of predictable chemical behavior. That particular functional group, whatever compound it's found in, undergoes the same type of chemical reaction. So that's what's so important about it. Categorizing. Let's begin by looking at the first of the functional groups a little closer, called alcohols. The alcohol functional group is the OH, known as a hydroxyl group. Now remember, learning in inorganic chemistry, we had a polyatomic ion, OH negative 1. Its name was called hydroxide. In inorganic chemistry, if we saw NaOH, this hydroxide is how we knew it was a base. I want to make it, bases are the opposite of acids. HCl, hydrochloric acid. Opposite of an acid is a base, and this particular ion, when dissolved in water, makes a basic solution. Inorganic chemistry. I want us to shift gears. Remember, we're in organic. An alcohol has a functional group hydroxyl. It is not a basic solution. It does not ionize when placed in water. So very important to make that distinction. Even though I'm seeing an OH, it has nothing to do with making it a base, as we learned in an acid-base chapter in a previous inorganic lesson. What we're looking at now is at a functional group, a hydroxyl group, turning it into an organic molecule known as an alcohol. Now, we have functional group, RH, structural formula, or a condensed formula. All of them indeed kind of showing the same thing. The OH functional group, hydroxyl functional group, making it an alcohol. Alcohols may be primary, secondary, or tertiary. Now let's talk about that a little more specifically. Alcohols are classified as primary, secondary, or tertiary depending upon the number of carbon atoms bonded to the carbon that bears the hydroxyl group. Let's take a closer examination. Right here in the first structure, this carbon has only one carbon attached to the carbon that contains the hydroxyl functional group. This carbon is the only carbon attached to the carbon that bears the functional group. That is why it's known as a primary alcohol. In the second structure, the carbon that bears the functional group, the OH functional group, contains 2 carbons attached to the carbon that bears the functional group. It is known as a secondary alcohol. And in the third example, here is the carbon that is attached to the functional group. It contains 3 carbons attached to the carbon that bears the functional group. It is known as a tertiary alcohol. So really just kind of dividing primary, secondary, or tertiary alcohols based on the number of carbons that are attached to the carbon that bears the hydroxyl group. Very important to be able to categorize primary, secondary, or tertiary alcohols. Let's do a little practice here. It says we're going to draw a Lewis structure and condense structural formulas for the 2 alcohols with the molecular formula C3H8O. So in other words, how can we arrange 3 carbons, 8 hydrogens, and 1 oxygen to come up with 2 possible structures for an alcohol? Well, the first thing that comes to mind is we're going to attach the 3 carbons straight. And if I do so, I can create what's called a primary alcohol. Of course, every carbon then needs to fill out its octet with the attached hydrogens. Remember, one of the hydrogens must attach to the oxygen to create the hydroxyl functional group. It must be an alcohol with an OH attachment. By arranging CH3, CH2, CH2, OH in a structural formula, we've created a primary alcohol. Now take a look at what we've done. We've done CH3, the first carbon with 3 hydrogens. CH2, the second carbon, has 2 hydrogens. CH2, the second carbon bearing 2 hydrogens, and then OH, the functional group. Now to complete the octet on the oxygen, we would need to draw in 2 dots on the top and bottom to give it the octet, so that every atom has indeed achieved the number of electrons like its noble gas. The primary alcohol has 1, 2, 3 carbons in a row. I'm just kind of throwing this out here for now. 3 carbons, we'll learn, has the prefix propane. Taking off the E and adding on the OL ending for the alcohol, we have an alcohol called 1-propanol. On the first carbon, and I'm going to count the carbons where the attached functional group is given priority. Carbon number 1, 1-propanol. Now remember, if I had drawn this structure, and I'll just kind of draw it down here, and the OH happened to be on this side, would it really matter when we name it? And the answer to that is no, because carbon number 1 is always given the priority to that it contains the functional group. This would still be called 1-propanol. Getting a little ahead, but it never hurts to seed future lessons in nomenclature for alcohols. Now, how else can we draw this structure? 3 carbons filling in the 8 hydrogens, and then leaving us an OH group for functional group. So I know that we had 3 carbons. In our primary alcohol, we actually attached the OH to either one of the ends. But what if we attached it to the second alcohol, or to the second carbon, creating what's called a secondary alcohol? Let me finish drawing in those H's. So we would have a structure that looks like this. And again, you might see that written as just simply OH and not necessarily have to put that single bond in that functional group hydroxyl. It's assumed to be there. So here we would have CH3, CHOH, CH3. Putting in order, reading from left to right as you do any text, the functional group OH being a secondary alcohol. Notice it's secondary because the carbon that bears the functional group contains 2 carbons that are attached to it. Here we had just the carbon that contains the functional group actually had just one other carbon attached to it. So it's why it's called a primary alcohol. Now notice here, if we were going to name this, might as well just practice, the carbons starting at the end of either chain are going to create the lowest number right there. It doesn't matter if I number 1, 2, 3 right to left or 1, 2, 3 left to right. The alcohol is being placed on the second carbon. This would be called 2-propanol. And again, it's coming, just kind of seeding in next lesson. 2-propanol. When we look at the answer, you can see that they have on page 315 of our text had drawn similar structures for us as well. A secondary alcohol and a primary alcohol drawn as condensed structures, and then they turn that into a little ball and stick model as well. Notice this right here is the functional group, the OH. Oxygen generally given to us in red, the hydrogens will be in light blue. So we have a structural group, primary and secondary, for our propanol alcohols. A second category of functional groups are known as the amines. Amines are compounds that contain an NH2 group. They could be primary, secondary, or tertiary, depending upon the number of carbons that are attached to the nitrogen that bears the functional group. Let me repeat that. They can be primary, secondary, or tertiary depending upon how many carbons are attaching to the carbon that bears the functional group. I think I said it better that time. Let's practice, see if I can make sense of that. Here we have a primary amine, CH3NH2. If I were to draw that structurally, we'd have CH3NH2. And I do have a lone pair of electrons to complete the octet on that primary amine. The nitrogen is attached to 1 carbon. The nitrogen is attached to 1 carbon, making it a primary amine. When I look here, dimethylamine, drawing the structural formula, we have CH3NH and then CH3, fitting in those dots on the nitrogen. Well, look here, the nitrogen, the amine functional group, now has 2 carbons attached to it, making it a secondary amine. Subbing out one of the H's and putting that on as a second carbon. We'll soon learn that methyl means 1 carbon. That prefix meth means 1 carbon on each of the chains. And of course, a tertiary amine would simply show a structure similar to this, where we have 3 hydrogens. This is a methyl. We still have a dots up here. 3 H's on these each, giving us trimethylamine, a tertiary amine. So very similar to how alcohols are named, amines will follow that same category. Depending upon the number of carbons attached to the nitrogen in the functional group will make it determine if it's primary, secondary, or tertiary. So let's try the same idea. Let's draw 2 primary amines. Draw a condensed structural formula for the 2 primary amines with molecular formula C3H9N. This is the middle is misleading where it says 2 primary amines. Well, I think they're talking about 2 primary structures. One will be primary, one will be secondary. Let's take a quick peek. Draw these structures out. Suppose, oh no, I'm thinking wrong. I can get these to be 2 primary. So this is key. 2 primary says no matter what I do, I can only have 1 carbon attached to the nitrogen. So let's get a bearing here. We got 3 carbons in a row. To make them both primary, which means I can only have 1 carbon attached to it, one obvious structure is to put it at the end. So to fill in the rest of that structure, we'd have CH3, CH2, CH2, NH2, CH3, CH2, CH2, NH2. That would give us one example of a primary amine. Now I can think of a second way, going back to this backbone of 3 carbons in a row. I can also place it up here, and that nitrogen with its functional group for amine, 1, 2, 3, we could write this as CH3, CH, NH2, CH3. And this is also a primary amine because the nitrogen is still just attached to 1 carbon. But I'm placing it on the second carbon in the 3-branch chain. And now we've created 2 different structures by placing the amine group either on the first carbon or on the second carbon, making them both primary, but the location of the NH2 group would indeed be different. What if I had a structure something like C4H11N? What might be 3 secondary amines with molecular formula? We're looking for 3 secondary amines. How could we arrange these to get 3 structures that are secondary? Well, let's put our heads together. What if we said one, 2, 3. So I can put the nitrogen right smack in the center of both carbons. 1, 2, 1, 2, 3, 1, 2, 1, 2, 3. Again, every one of those bonds leading to a hydrogen, and there would be a lone here. That's an example of a secondary amine that meets the criteria. I put them right smack in the center. What if I put it with something like this? 1, 2, 3. And then filling out those hydrogens, give me a secondary amine. What else could we come up with? One more where I can only attach to 2 of those 3. Now I know that this one, I might be tempted to just put it at the other end, but that actually ends up to be the same structure but just flipped. So what if 1, What if we did something like that and just change out the order in which the carbons bond? I could still draw a structure that's just a branch chain for the carbon. 1, 2, 3, 4 carbons. And the secondary structure for amine still only has 2 carbons attached to it. So instead of creating just a 3-carbon straight chain, what if I just branch that chain? And we'll learn that that's an isopropyl, kind of a iso grouping. We'll learn more about that structure later. But again, I'm allowed to branch that chain as well to create yet another example of a secondary amine. The solution for the model that we just talked about, matching up on page 316 to our example of 2 versions of primary amines for the formula C3H9N. Checking your work from what you just drew with my little talk, draw against this particular solution guide. Make sure they indeed match. Let's talk a little bit about aldehydes and ketones, 2 different functional groups, but we'll talk about them together here since each of those functional groups contains a carbonyl group. Carbonyl is C double bond O. If the aldehyde contains a carbonyl group bonded to a hydrogen, in other words, it's going to be at the end of a chain. The simplest, of course, would be formaldehyde. The carbonyl group bonded to 2 hydrogens. So in other words, that structure for formaldehyde, the simplest of functional groups, would have a carbon, double bond O, H, H. The simplest aldehyde. I could also, you just keep drawing if you had 2 carbons in a row, and the end carbon always has a hydrogen at the end, makes this an aldehyde. So the simplest functional group places a C double bond O at the end of a carbon chain. If that carbonyl group, C double bond O, is bonded to 2 carbons anywhere else but at the end of the chain, we call it a ketone. A functional group that places the carbonyl group, C double bond O, at the end of a chain will always have a hydrogen. Aldehyde. If the functional group C double bond O, known as a carbonyl group, is anywhere but at the end of the chain, attached to 2 carbons instead of just 1, it is known as a ketone. Let's try to draw some structural formulas for 2 aldehydes with the molecular formula C4H8O. Now it says aldehyde, so I know that it has to be at the end of a carbon chain. One of the first things I think about then is a straight chain. Put 4 carbons in a row, that's a straight chain. That 4th carbon will contain the carbonyl functional group, C double bond O, filling in the rest of the carbons with hydrogens. You realize that even though I'm not drawing these, I know that they're there. And technically, we know that these have a couple of dots after them on the oxygen to fill its octet. What else might we draw? Well, I know that the aldehyde has to be at the end of the chain, so really my only other choice is to start branching this particular carbon chain. So instead of 3 in a row, let me just kind of get this straight. We've got OH has to be there. What if instead of going 1, 2, 3, we make another carbon come down? Well, that's too many. Oh, I have 4 carbons, sorry. I gotta start over. Please forgive, I'm gonna start fresh. So I have my first carbon, here's my have to have. Alrighty. So I have to have this as the beginning. Alrighty. Now what we drew before is straight chained. What if we branched this? So we have CH3, CH3. We still have 1 hydrogen here. Now let's kind of make sense of what we just drew. First one, CH3, CH2, CH2, COH. And that's telling me there must be a double bond there. This is not an alcohol. It's not a hydroxyl group. but it because it's not CO, this here is a double bond. Here we had this carbon, CH. Typically what you'll see is CH3 written in a parenthesis taken twice as the attachments here, and then COH. The aldehyde functional group branching the chain to come up with two different structures. Give you a moment to digest this slide. All you're doing now is checking the problem that we just worked. Make sure yours matches both structurally, probably a little bit cleaner than mine. I do notice that they wrote these in a reverse order, which I like better now that I think about it. I had written mine on the previous slide COH, and that might trip up beginning organic students thinking that looks like a hydroxyl group because it looks like that OH for the alcohol, but that's wrong. It's not. So let's get that. I like that. Let's CHO lets me know the hydrogen is actually attached to the carbon and not the oxygen. So this looks like a much more acceptable way to let us know that it indeed is the aldehyde functional group and not the alcohol. And again, same story over here. CHO lets us know the hydrogen's attached to the carbon, not the oxygen. So that functional group there is the aldehyde, not the alcohol. Here's some carboxylic acids. COOH is the organic acid, and they get that from really two separate functional groups put together. Carbonyl, C double bond O, and hydroxyl, the OH group. Put that together and you get carboxyl. In its condensed structural formula, you might see it written as CO2H, but most often I see it written as COOH, letting you know that it has two functional groups together, the C double bond O, carboxyl, and the OH, hydroxyl group. So a common, this is vinegar, acetic acid, CH3, COOH, shows the functional group called carboxylic acids. Carboxyl group, hydroxyl group, put together, and we get carboxylic acids. Considering carboxylic acids, let's practice drawing for a single carboxylic acid with a structure C3H6O2. What might that look like? Well, I can see that the three carbons will go in a row. To make it into an acid, I see that I'm going to have to put the COOH functional group. The functional group carboxyl and the functional group hydroxyl. So it gives us two functional groups together called carboxylic acids. I'll clean that up. C, C, C. Double bond O going north. Single bond OH, filling in the dot structure. We get this structure, CH3, CH2, COOH. COOH, the organic acid. That must be at the end of a group. That has to be the terminal carbon. Okay, so no other place to put, to put that within the structure. COOH will always be at the end of your carbon chain. And indeed, ours did match. Take a look at this slide. It's the solution to what we just drew. The last of our functional groups we'll talk about are called carboxylic esters. Carboxylic esters are derivatives of carboxylic acids, but the hydrogen at the end has been replaced by another carbon chain. So think about carboxylic acids, and I'll just kind of repeat myself there. COOH gave us the carboxylic acid in which we had some kind of hydrocarbon chain. We said this had to be at the terminal carbon to make it an acid. carboxylic acid. But now what we're going to do is eliminate this particular hydrogen, the terminal hydrogen, and replace it with some other carbon chain. And we'll come up with an ester. A carboxylic ester is a derivative of a carboxylic acid, but we're taking off the terminal H and replacing it by some other carbon chain. So here's an example. We have methyl. This is the group here. Acetate, and that's 2 carbons. 1 carbon, methyl. 2 carbons, acetate. Hear the N there, A-T-E, acetate. It's an ester. Thinking about how they wrote that, CH3, COO, CH3. COO, this section here, when I see that, I have to kind of go into structural format. That oxygen, one will be a double bond, one will be the oxygen that's now attached to another carbon. Okay, so it is a derivative. I'll get that word out. And at this point,